Welcome back. After introducing the Laplace transform, it is natural to ask, is there an inverse function that can bring us from the Laplace transform space to the original time space? And that is called the inverse Laplace transform. In this video, I will introduce inverse Laplace transform and give some examples of doing them. First, let us define inverse Laplace transform. If we have a big f of s that represents the Laplace transform of the real time domain function small f of t, then the small f of t is called the inverse Laplace transform of the big f of s. And in terms of symbols, it means that if we have the Laplace transform, then the inverse Laplace transform of the Laplace transform function is the original function, which is written in this form, so that the effect cancels out. This is similar to calculus, where taking the derivative and its inverse operation is taking the integral. And if you take the integral of the derivative or the derivative of the integral, then the effect cancels out. Notice that the inverse Laplace transform is also linear. Therefore, we can extract the constant out, and then we can also break down each individual term with addition. For example, if we have the inverse Laplace transform of a function, say 5 of t plus n e to t, then I can write it as 5 inverse Laplace of t inverse Laplace e to t. So that greatly simplifies the calculation for addition of terms. The calculation of inverse Laplace transform is even more tedious than calculating the Laplace transform. You can notice that because I have not given a formal mathematical definition of inverse Laplace transform, rather than saying it counters the effect of Laplace transform. So as engineers, we use tables created by mathematicians, so we can use the table from Seborg in reverse. For example, if we have the Laplace transform function, we can take its inverse and it will give us the inverse Laplace transform, and so on. For example, if I see a function 1 over s minus a, I can take the inverse Laplace transform on that and get e to the a of t. Now let us practice using inverse Laplace transform with the table. So first, let's evaluate the inverse Laplace transform of 1 over s of 5. First of all, we can notice that in the denominator we have s of n plus 1. So we can match the terms, so n plus 1 equals 5, so n equals to 4. And then at the top we need n factorial, but at the top we only have 1. So now we need to use the trick of multiplying by 1. By multiplying by 1, I mean that you can write it as 1 over s to the 5th equals to 4 plus 1. And then by multiplying by 1, I want top and bottom to have the same number. And I want it to be n factorial, which is 4 factorial, the top and bottom. And then I can bring this 4 factorial at the top to here, so that I have 1 over 4 factorial s 4 plus 1. And then we can notice that this term can be written using the table. So we have 1 over 4 factorial, and because n equals to 4, we have e to the 4. And we have solved the problem. And similarly, to evaluate the inverse Laplace transform of 1 over s squared plus 7, we notice that a here, there's an a square, so a squared equals to 7, a equals to square root of 7. So in order to get the a at top, we need to multiply by 1. So I have 1 over s squared plus 7, which is square root of 7 squared. We want to multiply by 1. To do that, we multiply by square root of 7 top and bottom, bring this one inside 1 over square root of 7, square root of 7 over s squared plus square root of 7. And the latter term, we can rewrite it using the table, which is sine a of t, where a equals to square root of 7. We have solved it. Now let us look at a more complicated example where we have terms, addition terms at the top of the numerator. To recall from the table, we have the inverse Laplace transform of a over s squared plus a squared is sine of at. And the inverse Laplace transform of s over s squared plus a squared is equal to cosine. These two are different because a is a constant, but s is the variable in the Laplace space. They're very different. And to evaluate the expression, negative 2s plus 6 divided by s squared plus 4, we can write it out so that they have the common denominator, square plus 4, but the term at top can be separated. And using the linearity of inverse Laplace transform, we can have the inverse Laplace transform of the first term, where negative 2 is a constant, that I can get it out. Inverse s divided by s squared plus 4, plus 6 is a constant, I can get out. And inverse Laplace transform 1 over s squared. In the first term, we have s at the top, so we use the cosine one. Cosine of at, where a is equal to a squared is equal to 4, so a equals to 2t. Plus the inverse Laplace transform of 1 over s squared plus 4, that we use the sine property. 4 equals to a squared, so a equals to, we have sine 2t. That is our. Notice that we changed from the Laplace space, which is S space, to the real time space. By real, I mean real world time space. The inverse Laplace transform expressions aren't always that easy to solve. And if we encounter a denominator that has two terms multiplied to each other, we will need to use a technique called partial fractions, where we have the multiplied terms equal to some term plus the other term. And we assume two constants, and we need to solve for them. In this example, we have s minus 1 and s plus 4 at the bottom. And we assume that they can be separated with s minus 1 plus s plus 4. And at the top, we have constants assumed. Then we want to multiply by 1 for each term. Multiply by 1, I want to let them have the same denominator as before. So in the first term, I multiply by s plus 4 for top and bottom. And for the second term, I want to multiply by s minus 1. Notice I haven't done anything because these are multiplying by 1. So let's multiply them in. S minus 1, s plus 4. Notice that they all have the same denominator of s minus 1 multiplied by s plus 4. So I can collect the numerator, multiply them out. As plus 4a plus b times s minus b times 1. And if we look at the left-hand side, the right-hand side and the left-hand side all have the same denominator, and therefore they must have the same numerator. And notice on the right-hand side, I have s terms and constant. S terms has a and b. The constant terms are 4a minus b. The left-hand side, I only have a constant term. I have no s term. If we want to write out s term, it is 0 times s, because there's nothing about s. So we can match the coefficient, where the 0 corresponds to a plus b, and the constant 1 corresponds to 4a minus b. And that will give us a linear system of equations. And the first equation can be written as a equals to minus b. Substitute to the second equation, and 1 equals to negative 4b minus b. 1 equals to negative 5b. So b equals to negative 1 over 4. Therefore, a is the minus 1 over 4. We can plug in to 4 and get the final expression of 1 over 1 minus 1 over b s plus 4. Now we can proceed to find the Laplace transform, inverse Laplace transform of that expression. Inverse Laplace transform the original expression can be reduced to partial fraction. And then we use the linearity property, pull out the constant, and then separate each term, evaluate it individually. Now we want to find things that look this in the table. And from the table, you can find that the inverse Laplace transform of s plus a 1 over that equals to e to the negative 8. In the first case, we have s minus 1, a equals to minus 1. Plug it in, e, negative negative is a plus, so e to the t, and that's 1 over 5, e to the a equals to, so e to the minus 4. And that is our partial fractions can be determined more easily with the Heaviside expansion or the Decomposition method. To illustrate that, it is the best to do it through an example. In this example, we want to look at the partial fraction expansion of 1 over s1 times s plus 1. And we set up the partial fraction expansion with a minus s minus 1 plus b divided by s plus 1. And then we want to multiply both sides by one common denominator term of s plus a. For example, we can do it first for s minus 1. So we multiply both sides by s minus 1, both things minus 1. And then we see that these terms cancel out. So on the left, we have s plus 4 equals to, these terms cancel out, a plus b s minus 1 s plus 4. And then the third step is to evaluate at a s equals to minus a. In this case, a equals to -1. So we want to evaluate s equals 1 so that we can make s minus 1 0. So that substitute s equals to 1, we have 1 divided by 1 plus 4 equals to a plus whole term goes out because s minus 1 equals to 0. So we can calculate a equals to 1 divided by 5. And that is the coefficient for the first. Looking at it in another way is that if we have the original term and if we cover up the denominator term s minus 1, we cover it up, then cover it up, and then we evaluate at s equals to 1. Then we have 1 divided by s, which is 1, is 4, and that is the coefficient for that term. There are two ways to view it. The cover-up method is far simpler to work with, but the mathematical foundation is given by the Heaviside expansion. Notice that this method has a limitation that it can only be used with the rational functions of s with distinct linear factors in the denominator. If the denominator is more complex than these distinct linear ones, then this method cannot work. Let us finish up the problem by identifying the coefficient for the second term. So we first set up the partial fraction expansion s minus 1 is plus 4 1 over equals to a divided by s minus 1 b divided by s. And then to get the second term's coefficient, we multiply both sides by plus 4. And then cancel out things. Left with 1 divided by s minus 1 equals to a s plus 4 s minus 1 plus b, as they cancel. And we evaluate so that s plus 4 equals to 0. S should be minus 4. Substitute that in. 1 divided by minus 4 minus 1 is minus 5 equals to, because we have already set s plus 4 equals to 0, that term is 0 plus. So b is equal to minus. Similarly, we can use the cover-up method, which is a little bit simpler but still the same. We want to cover up the target so that we have 1 divided by s minus 1, and we evaluate this at s equals to negative. So that is 1 divided by minus 4 minus 1 is over minus 5, and that is the second. We can verify this with our original method, where it gives a equals to 1/5, b equals to minus 1/5, and they check out. Notice we still haven't finished the problem yet. We had 1a equals to 5, b equals to minus 1 over 5. That gives us the partial fraction expansion 1 over 5th is minus 1 minus 1 over 5th is 4. And we want to find the inverse Laplace transform. So we use the linearity property, constants taken out, and then each individual terms being inverse. And again, we look at the table. The table gave us that inverse Laplace transform of 1 over s, a equals to e to the negative at. In this case, we have first one, a equals to -1. E to the -1 is +1. And the second one is e to the -4. That is the same as we determined before. Let's finish with a more complicated example to illustrate how easy it is to use the cover-up method or the Heaviside expansion. So for this partial fraction expansion, s squared plus 6, 9 divided by 3 linear factors. They're distinct. So we can use the cover-up method. First of all, let us cover up s minus 1. Let's write out the partial fraction s minus 2 plus t. Let us first cover up s minus 1. So we have s squared 6s plus divided by 2s plus 4. We evaluate so that s minus 1 equals to 0, so s equals to 1. And then 1 squared plus 6, 1 minus 2, and that is divided by -5. And then let us cover up the second term. The first term is a. Second term, square plus 6s minus 1. S minus 2 is being covered, and s plus 4. We evaluate so that the cover-up term equals to 0, so s should be 2. Evaluate at 2, we have 4 plus 12 plus 9 divided by 1 multiplied by. So we have 15 plus 9, 25 divided by b, second coefficient. Lastly, let's cover up the third term. We have s squared plus 6s minus 9 divided by minus 1 s minus 2, and the third term is being covered. We cover that so the last term equals to 0, so s should be equal to -4. Substitute in minus 4 squared 16 minus 24 9 minus 5 times. We have 30 at bottom. At the top we have 1. And we have the third coefficient. So we can fully describe this rational function with its partial fraction decomposition. Just plugging in the numbers. Right. That's the first part of the problem, partial fraction expansion. And the second part is to Laplace transform everything, inverse Laplace transform. And then we can use the linearity property, take out all the constants, and then do it term by term. Rewriting this for clarity. And then again, we use the property that the inverse Laplace transform of 1 over s plus a equals to e to the negative. Just be mindful of the sign. So here we have a equals to -1. Minus is. Second term we have a is equal to -2 plus 2t. Third term we have a equals to 4 e to the negative. This is our final inverse Laplace transform. So in this video we have covered the definition of inverse Laplace transform in simple terms. We covered the table for inverse Laplace transform, and we look at partial fraction expansion using traditional general method and Heaviside expansion and cover-up method.